calculate the demand load for 5 12.4 kilowatt ranges, we will proceed in a step-by-step manner. Firstly, determine the individual load. Each range has a specified load of 12.4 kilowatts. Secondly, calculate the total load. This is done by multiplying the number of ranges, which is 5, by the individual load of 12.4 kilowatts. Therefore, the total load equals 5 multiplied by 12.4 kilowatts, resulting in 62 kilowatts. Thirdly, apply the demand factor. The demand factor is a percentage that represents the expected actual load compared to the total connected load. For commercial electric ranges, a typical demand factor is 70%, or 0.70. To find the demand load, multiply the total load by the demand factor. Demand load equals the total load of 62 kilowatts multiplied by the demand factor of 0.70, which equals 43.4 kilowatts. Therefore, the demand load for 5 12.4 kilowatt ranges is 43.4 kilowatts. Now, let's delve deeper into the concept of demand factors and their significance in electrical calculations. The demand factor is a crucial element in determining the appropriate size of electrical service for a building or facility. It accounts for the fact that not all electrical loads will be operating at their maximum capacity simultaneously. This allows for a more efficient and cost-effective design of the electrical system. Different types of loads have different demand factors. For example, lighting loads typically have a higher demand factor than receptacle loads because lighting is more likely to be used continuously. Electric ranges, as we've seen, also have specific demand factors based on their type and application. The National Electrical Code, or NEC, provides guidance on demand factors for various types of loads in Article 220. It's essential to consult the NEC and any local electrical codes to ensure accurate and compliant demand load calculations. The NEC provides tables and guidelines for calculating demand factors based on the number and type of appliances. For example, Table 220.55 in the NEC provides demand factors for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances over 1.75 kilowatts rating. These demand factors vary depending on the number of appliances and their individual ratings. Let's consider an example using NEC Table 220.55. If we had 3 12 kilowatt ranges, the demand factor would be 80% according to the table. Therefore, the demand load would be 36 kilowatts or 3 multiplied by 12 kilowatts multiplied by 0.80. It is important to understand the difference between demand factor and diversity factor. While both are used to estimate load, they are applied differently. The demand factor, as we've discussed, is the ratio of the maximum demand of a system or part of a system to the total connected load of the system or part of the system under consideration. It is always less than or equal to 1. The diversity factor, on the other hand, is the ratio of the sum of the individual maximum demands of the various subdivisions of a system to the maximum demand of the complete system. The diversity factor is generally greater than 1. Applying the correct demand factor is crucial for accurate electrical design. Underestimating the demand load can lead to overloaded circuits, voltage drops, and potential safety hazards. Overestimating the demand load, on the other hand, can result in an unnecessarily large and expensive electrical service. In addition to the NEC, local electrical codes and utility company requirements may also specify demand factors for certain types of loads. It's essential to consult all applicable codes and regulations to ensure compliance. When calculating demand loads for commercial kitchens or restaurants, it's important to consider all of the electrical appliances that will be used, not just the ranges. This may include ovens, fryers, grills, dishwashers, and other equipment. Each appliance will have its own individual load and demand factor. To determine the total demand load for the kitchen, you will need to calculate the demand load for each appliance and then sum them together. It is also important to consider any future expansion or changes to the electrical load. If there is a possibility that additional appliances will be added in the future, it's a good idea to oversize the electrical service to accommodate the increased load. This can save time and money in the long run by avoiding the need to upgrade the electrical service later on. In summary, calculating the demand load for electrical ranges and other appliances requires a thorough understanding of demand factors, the NEC, and local electrical codes. By following a step-by-step approach and consulting all applicable resources, you can ensure accurate and compliant electrical design. Let's now address some potential issues that might complicate the calculation of demand load. One common issue is the presence of different types of ranges with varying power ratings. In such cases, you would need to calculate the individual demand load for each type of range and then sum them up to obtain the total demand load. Another issue arises when the ranges are not used simultaneously. In a commercial kitchen, for example, some ranges might be used more frequently than others. To account for this, you can use a diversity factor in addition to the demand factor. The diversity factor reflects the probability that all ranges will be operating at their maximum capacity at the same time. Obtaining accurate information about the usage patterns of the ranges is crucial for determining the appropriate diversity factor. This information can be gathered through surveys, interviews, or historical data. Furthermore, the installation method of the ranges can also affect the demand load. For example, if the ranges are installed with energy-saving features such as automatic shut-off timers or power-limiting devices, the demand load might be lower than the calculated value. It is important to consider these features when determining the appropriate demand factor. Let's look at another example. Suppose we have two 10 kilowatt ranges and one 8 kilowatt range. According to NEC Table 220.55, the demand factor for three ranges is 80%. However, since the ranges have different power ratings, we need to adjust the calculation. Firstly, calculate the total connected load, which is 10 kilowatts plus 10 kilowatts plus 8 kilowatts, which is 28 kilowatts. Secondly, apply the demand factor of 80% to the total connected load, resulting in 28 kilowatts multiplied by 0.80, which equals 22.4 kilowatts. Therefore, the demand load for the three ranges is 22.4 kilowatts. It is important to note that the NEC provides specific rules for calculating demand loads for ranges in dwelling units. These rules differ from the rules for commercial ranges. For example, NEC Section 220.55 provides a table for calculating the demand load for household cooking appliances based on the number of appliances and their ratings. This table allows for a reduction in the demand load based on the assumption that not all appliances will be used simultaneously. In addition to ranges, other types of cooking equipment such as ovens, cooktops, and microwave ovens also contribute to the overall demand load. It is important to consider all of these appliances when calculating the total demand load for a kitchen or cooking area. The NEC provides specific rules for calculating the demand load for each type of appliance. Furthermore, the type of fuel used by the ranges can also affect the demand load calculation. Electric ranges have a different demand profile than gas ranges. Electric ranges typically have a higher instantaneous power demand than gas ranges, but gas ranges may have a higher overall energy consumption. When calculating the demand load for a mixed fuel kitchen, it is important to consider the different demand profiles of the electric and gas appliances. In some cases, it may be necessary to install separate electrical services for the electric and gas appliances. Another factor to consider is the presence of other large electrical loads in the building. If the building has other significant electrical loads, such as HVAC systems, lighting, and motors, it is important to coordinate the demand load calculations for all of these loads. The total demand load for the building should not exceed the capacity of the electrical service. It is also important to consider the voltage drop in the electrical system. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the beginning of the circuit. Excessive voltage drop can cause appliances to malfunction or operate inefficiently. The NEC provides guidelines for limiting voltage drop in electrical circuits. When designing an electrical system, it is important to select conductors that are large enough to minimize voltage drop. In addition to the NEC, other industry standards and best practices can also provide guidance on demand load calculations. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards on electrical design and power systems. These standards can provide valuable information on demand factors, diversity factors, and other aspects of demand load calculations. It is also important to stay up to date on the latest changes to the NEC and other relevant codes and standards. Electrical codes are constantly evolving to reflect new technologies and safety concerns. By staying informed about the latest changes, you can ensure that your demand load calculations are accurate and compliant. In summary, calculating the demand load for electrical ranges and other appliances is a complex process that requires a thorough understanding of demand factors, diversity factors, the NEC, and other relevant codes and standards. By following a step-by-step approach and consulting all applicable resources, you can ensure accurate and compliant electrical design.